Let's start with this. This is something which you probably recognize. This is the classic basic three-tier architecture that everything is built on. The trouble is that we are not building things on it. We have found this to be not particularly useful. Over a number of developments, over a number of separate websites and over a number of separate services, we've found that this has been evolving into this. Now, can you see that? Is the projector up to the job? What we've got is actually 5 layers going on, not just the 3. What we found was that the data layer, the assistance layer, was splitting into 2. The business layer was developing every single time an API across the front of it. And then the application actually split into 2, which was the application proper and the presentation layer on top of that. Now, what are those for? The application is exactly what you expect it to be. It is where you get the experience of the service. But what we're developing out of the application, what it's producing, is something which we are jokingly calling HTML6. You heard it here first, folks. The point about HTML6 is that it is pure content. It's the simplest, most pithiest expression of the user experience that we can possibly arrange. What we then do is we use the presentation layer to add information onto the outside of that, which is effectively the Chrome, the user experience, all of the things which make it into a real usable service. The point about that is that it's negotiated in exactly the same way that the language is negotiated. So the presentation layer knows what the client is, so it can change what's being delivered. So if you can deliver a native service to IE, to Chrome, to whatever. If you're on a mobile, then it can tailor that service onto the mobile. If you're working on ancient Russian laptops in African Wi-Fi, then it'll handle that too. It'll seamlessly downgrade the service in order to fit into the resources it's got available. And we've found more and more that this is an important layer to have. But that's not what we're going to talk about today. The API turned out to be very important because it helped us to define exactly what the business layer was. The business layer delivers the transactions as normal, but by creating an API, we can concentrate the whole of the front-facing security at that layer. Everything that's above that layer is all public, but everything that's below that layer is all secured. And we can create in all sorts of formal ways. We have a language to describe what the API is and how it enforces the security, and then how it approaches the business layer. The business layers now turn out to be quite thin, but we're not going to talk about that either. What we're going to talk about is down here, and this is the data in the data virtualization layer. The problem that we have is this. In the old days, when you were building a service or you were building a website, you'd get yourself a database and you'd slap it in and then you'd make SQL calls into it. Nice and easy. But the problem now is that the data doesn't reside in one single database. It can be all over the place. So we can run a database, but actually we might have several backup services running at the same time. One of the use cases which got this started was user authentication. Now, in order to get through the API, let me give you a better view of this. In order to get through the API, sorry, that's better. You need to be able to deliver tokens. It creates a ticket to ride. And this is effectively your session ID. There's a whole lot of stuff attached to it, but it's integrated with the security in the API. But where does that come from? We need to authenticate. We have, as part of our data layer, we have an authentication service. So the process is you would deliver your user credentials, get back the token, then continue to work with that token in all of your subsequent transactions, which is fine as long as you're using our service. But if you want to use an OpenID or single sign-on or something like that, then you're not using our service anymore. Now, what we wanted to do was to unify that at the virtualization level. So we wanted to say from the virtualization layer, we have an authentication service. It's in some repository somewhere. We don't control it, or maybe we do control it, but it's up to the virtualization layer to go and find it. Does that make sense? Now, we've got lots of other examples of these sorts of uses. We have examples where we have data sitting in our database, but we might have a master server elsewhere. So we need to be checking for updates. Or perhaps we've got the whole lot off-site. And so, we've got our top-level structures elsewhere, and then we've got our local structures held locally. we need to be able to resolve that, and we need to be able to resolve that in a unified manner, in such a way that the business layer doesn't actually know what data source it's talking to. So does that make sense? Have any of you actually experienced this problem of trying to unify these things?
I think in our company they've tried to address it by sticking everything in one massive database, which doesn't work very well.
No, it doesn't. On the other hand, sticking it into separate databases is also pretty hard. Because then you've got the problem that they're all over the place. The kind of approaches that you use to talk to the databases don't work. You can't just take a chunk of SQL and expect it to work, because you might not be talking to a SQL database at all. You might not even be talking to a database. It might be delivered as a service, and so you have to get involved in a dialogue to get your data out. So, and as people are moving more and more towards these transactional type things, and as people are taking their table-based databases and producing document databases, this problem of trying to unify this and trying to deliver a coherent vision of what data is becoming more and more difficult. So, hence the data virtualization layer. Now, what we have to do to create this is two things. We have to create a concept of what data is, which will represent all of these different kinds of storage, all these different kinds of persistence. And we have to be able to represent that to the business layer in a single, unified, coherent form. So it's what's exposed at the top. That's what we have to do to design this. The other thing that we have to do is we have to find some way of coupling that model of data to the actual types of data, the actual data delivery that we have available to us. And obviously, we have to do that with some knowledge of what the underlying representations are. Does that make sense? So that's what we're going to address. We're going to talk about those two things, what the data model is and how we connect it. Now, I spent some time trying to work out how to express this data model. I was thinking, shall I give you a bunch of representation? Shall I give you a bunch of mathematical rules? And I was thinking, no, the easiest way to do this is with code. I'll show you some actual working code. And because of that, this is probably going to be one of the most concrete presentations in the whole week. Everybody else is doing box diagrams. I'm showing you code. So, some basic principles. What we've got here is that it is not object-based. In fact, let me tell you a few things here, because this is probably important. What we're not trying to do here is ORM or anything like that. The Ruby principle of don't repeat yourself doesn't apply here, because what Ruby is trying to do and what the ORM models are trying to do is to take what's in the table and create it in memory as an object and try and equate those two. Now, the problem is we might not have a table, we might not have a record, we might not have any schema at all. So that whole approach isn't working for us. We're looking at something different here. So what we have is, even though we're going to be representing this in an object type thing, it's not, the object itself does not represent the actual data as it's stored. We're doing something else with it. It's a more abstract notion of what it is. The other thing is that although most of the old data sources which you're going to be using, or which we were using, were all relationships, were all relational, the modern ones aren't. So what we need to do is we need to create a concept of data which is not relational, but nevertheless contains some concept of relationality in it, because a bunch of separate data is no use to you. You have to be able to put it together somehow. So we're trying to half do here what has been traditionally done in different ways before. So I just want you to keep this in mind. This is not ORM. This is not relational. It's sort of falling between everything. That's the model we're using. It's a concept of indexed containment. The index is what's going to appear all the way through this. And a lot of what we're going to be dealing with is how to manage those indexes. Let's look at some code, because that's the easiest way to explain this. And I wish I'd brought a pointer. Okay, what we're going to look at here is we're going to look at a concept of users. I started with talking about authentication. We're not going to authenticate. We're going to assume you've got authentication. But what we're going to do is we're going to talk to them. We're going to create emails and send them and receive them. We have this sense of a factory, or we have this sense of a namespace. In this case, it's users. So the user's namespace is going to give us access to this whole user's notion. So what we're doing is we're resolving a name. So we're finding me, and we're assigning it to a variable. And so this is the object that we've pulled out of the database. This is PHP, by the way, on the basis that everybody knows PHP. If you don't, does anybody not know PHP? Oh, really? Okay, it's really simple. You'll pick it up as we go along. Now, having found it, having found that object, then we can then work with it. It has two aspects to it, and you can see these being expressed here. Can you see the comments on the side?
Just about.
Sorry, it's on the stick. You'll see it on the slides on the stick. But basically, what's going on here is that having found that object, we're then printing it out in two different ways. And the two ways that we're printing it is the visible name and the internal name. And so the internal name is going to resolve to, in this case, 103. I just made that up. It just happens to be where it is in the table. And the visible name is going to be whatever has been associated, whatever visible name has been associated with that. So that's pretty simple. That's pretty straightforward. We just go to the database, get the record, and we've resolved it by name. But we can also resolve it by number. So all the users represents an array of every user that's known to the system. And that array is indexed by its, what in, for want of better words, is its primary key. This is its key index. Now, there are several things to understand here. There might be 1 million users in the database, and that array might be 1 million users along, but most of them are not instantiated. This process will instantiate that record or that object only when it needs it. It knows about the array, but what happens is the objects in the array go through this life cycle where they start off like virtual, known about, and then they become concretized, they become instantiated. And so in this case, because this record has already been instantiated by resolving it, then when we look it up in the all array, then it's the same object. It's identical. What that triple the triple means is identity. Okay, so far so good. You understand this idea of the collection and the actual objects. Now, what we're doing here is we are creating a new object, and we're creating it out of memory. This thing is purely in memory. It doesn't exist in persistent store at all. And what it is it's a means by which we can send an email to this user. Quite a lot of behavior attached to it, but fundamentally, this is an emailer object. Now then, you can't see the comments, which is a real shame, but the reason why this is interesting is because this has an interface which is a user contact interface, and we'll be looking at that interface in more detail later on. What that user contact interface does is it basically implements a send method, and that's all it does. But that send method is not a property of the database. It's a property of the object in memory. But what this thing doesn't know, and so we can have a lot of different things all implementing that same interface. So we can have an SMS sender, or we can have a carrier pigeon sender, or a Ouija board sender, or whatever. The point is that they are all things which can be identified in these terms. It doesn't have an address, because the address is not the property of the sender. Now, we can start adding properties to it. If we want to say how we want to send, if we want to attach a cost to sending or anything like that, we can do that there. But there comes a point at which we have to associate that with the user, and that is the point at which you do it. So here's the thing. This is the fundamental nature of the relationship. We've associated it by this index. So this index both belongs to this collection. Now remember, this was a single object which we got out of the user's collection in the first place. This itself is now a collection, and this is identified with that index in the collection. So here's the important thing. The email address is not a property of the emailer object. It is a property of the collection that it's in. But there's more, because by doing that, whatever that contact is, by placing it into this collection, which is instantiated, this is in the database. Now, this is in the database. So we've not only created it, we've not only associated, we've also committed it into the persistent store. You're shaking your head. Is this making sense? Okay, I'm taking this slow because I'm really trying to explain what this data model is. You can see this life cycle developing. Now, once it's committed, we can keep on adding properties to it, and that might cause a round trip to the database. Generally, it won't. Generally, these changes will be stacked up and they'll be committed all at once. But in theory, those could cause a round trip each time. And so now, we might have a whole bunch of these things, all different sending methods, all different addresses associated with them, and now we're really keen to get in touch with him. And so here is the point at which we actually do the send. And so this is happening entirely separate from the database. It's using a different service altogether. It's using the email service. Now, what we could do is we could have treated that emailing service as another repository. I mean, it's a null repository because it's just eating the messages. But in theory, we could have constructed a message object and assigned it to the sender using another index. Because it's just as reasonable for the sender service to be part of your persistent store, because it does create side effects in the real world, as it is to treat it as a function. But the only reason I'm treating it as a function now is to limit the scope of the demonstration. So does that make sense? We've now got this concept of data based on the indexes, but we've got at least 3 different kinds of repository going on here.
But it's still an object model.
This is still an object model as it's seen from the client application. And in fact, this is the kind of code that you would see inside the business layer. This is the business layer talking to the DB layer. Now, I want to say more about this committing process. Do you remember right at the top, I said that you go.
I really don't understand why you create this contact object.
You don't understand why we would create the contact object.
Because I've got an object from the database, and that has a data attribute that I want to use to send an email, right?
Yes.
So what virtualization am I getting, abstraction am I getting if I'm creating yet another object that represents the same thing? Am I not just duplicating objects on the application space, like whatever context the application is running in?
Right.
Now, if I've got a million things in the database, I've virtually created 2 million objects.
You've virtually created it, but you haven't actually created it. You only actually create them when you start looking at them.
So it's lazy initialization.
It's all lazy initialization. But more to the point, these contact objects probably don't relate to anything that's in the database at all. What we've done is we've got this consistent view of something which will get a message to the user, which relates to nothing in the database. That it might be a load of things in the database. It might be just pure inferred from what's in the database. It might be elsewhere again. The point is that the user's objects are real data rows. The contacts is a very complex, odd, vague idea of data rows, if at all. And then the messages are not data rows at all.
But what do we persist then? So when you say persist the contact object in the database as well, right?
Beg your pardon?
So at one point you mentioned that we are persisting the contact object back.
That's right. We're persisting the contact object into the database through the index. The important part of what is committed to the database is the index. Now, there may be stuff that's attached to the contact as well, which is committed somewhere else. But it's the index which is the important part. The index is what defines the commitment. It also controls other parts of the life cycle of the object. This is what I'm showing here. In the second line, I'm really sorry you can't see the comments here, but in the second line, what we did was we depicted the object both as a visible name, as a string, and as an ID. Now, in this case, the contacts, the 2 representations are the same. The index and the visible name are the same. It's the email address. But it means that if at this point we print it out, then there is no name. It has no identity, because at this point it's an object in memory, but it has no external independent identity. So at that point, its invoked name or its invoked value is null. But having been committed, the same thing will give you that result back. So the object itself understands that it's been committed. The object itself understands the index. So this index appears in two different places. It's not a separate thing in and of itself. It's a property which belongs both to the collection and to the client object, to the contained object. Does that make sense? So in a sense, it works like a shared key, except there may not be real objects on the end of it. So this is the notion of relationship, which runs right the way through. Finally, we can get rid of it. If you don't know PHP, unset is just delink, and then the garbage collector cleans it up. What the unset does in this case is it says there's now no longer anything sitting on that index, so that will uncommit the contact. The contact still exists. We still have it in memory, but it's now uncommitted. It's no longer in the database. It's no longer indexed. It's no longer committed. So we can...
So it's no longer in the database?
Whatever about the contact was in the database has now been removed, because the process of taking it out of the indexing means that it's now uncommitted. There's no way back to it. So at this point, the contact that we have up there doesn't have an invoked value. It doesn't represent anything in the database. There is no index. We still have the in-memory object, and we can assign it to somebody else. We can even assign it to the same person under a different index.
But the underlying database where it originally came from, obviously, that row is still there? Or?
No, it's gone. That's what the unset means. This is uncommitting it. Now, the object can refuse, in which case this will fail. But we'll come to that. Okay, that, in a nutshell, is the data model, the model of data and relationships. It is, we have these objects in memory, we have these relationships between them, and the relationship is expressed both as an index and as an identity, and those are kept in synchrony. Does that make sense? Would you like to ask me any questions about this?
What if the object is in multiple collections and you remove it from one? Does that...
Give me an example.
I think of one off the top of my head. I've got two collections, an employees collection and a friends collection, and the same person's in both, and they decide to leave the company. So,
Right, I see. So what you're saying is that if you have one row which is being referenced, say, through a cross-reference table into two separate containers. Well, in that case, the way it's represented here is as two separate objects. Now, you may have a single row, and you can access that single row using one single object. But if you take this object and you index it into one table, then you then can't index it into you index it into one collection. You then can't index it into another collection because it's already in there. That will fail. But what you can do is replicate the object and then put the new object into the new collection. And so now you've got the two objects. Internally, they're the same, but conceptually, at this level, they become two separate objects.
Sorry, just to follow up on that, if you then remove it from one collection, there's nothing linking to remove it in the other. So you decide to remove it as a friend, for instance.
Yeah.
He's still an employee, is that right? Give me that example.
Let me play back your question. You're saying that if we now have one row connected to two rows, which is now represented by two objects at this level, if we delete one object or if we unlink one object, what happens to the other one? That stays there. That's still connected to the row. The row is still in the database. It's only if you take that away completely and there's now nothing linking it that the row disappears. Does that answer the question you're asking?
In a way, I'm still trying to, because this is a completely different way of thinking about the objects in the data that I'm used to. So.
Yes, it is. I admit it is. But the reason why it's a completely different way of thinking about it is because we can't take the relational model because we might not have relations. We can't take a document model because we might not have documents. And we can't even take a transactional model because we might have a whole cascade of transactions in order to resolve the data. So we need to have a different kind of representation. Okay, any more questions at this point? Okay, good. Let me show you, Oh, this is terrible. Can't see a thing. This is supposed to be all coloured so that you can see what the
Can't we switch off just those lights?
Let's try that. It's a bit better. Can you still see me on the camera? Okay, I'll put them on again in a minute. All right. What I'm trying to show here is that this data, let's talk in abstract about data. It can exist in lots of different states for lots of different reasons. The fundamental distinction is whether it's been instantiated or not. And instantiated means it exists in memory in some form. If it's not in memory, then it may exist in the repository in some form, which is here. So we know about it, and it exists. And of course, the other alternative is it doesn't exist in memory and it doesn't exist in the database, and we don't really believe in it anyway. So that doesn't appear on here. Now, what happens is, when you start creating the objects, when you look at those large collections, which don't represent any rows at all, those root collections represent the entire database through some lens. When you look at the collection, then what you know about is all of these potential objects. They exist in the database, and they are indexed in some way. They've got some way of identifying them. When we start looking at them, at that point we instantiate them lazily, and they come into memory. Now, what comes into memory can be either a root object, which, as I say, doesn't represent anything which is really in the database. It can be uncommitted, which means it doesn't exist in the database, but it does exist in memory. Or it can be committed, which means it exists both in memory and in the database in some form. But we're still not promising that there's any correspondence between the memory objects and the database objects. As long as it's uncommitted, it doesn't have an index. The index is, by definition, null. We know that it exists in the database, we know that it's persistent because it has an index, and that is the key. We give it an index, it's persistent. It doesn't have an index, it's not persistent. So that's a really simple thing to keep in mind. Bear in mind that the indexing containers are all about lazy loading. So behind the scenes of what you're about to see, there's a lot of stuff which is anticipating what we're going to have to read, anticipating what we're going to have to do. The containers also contain a concept of filtering, almost a kind of XPath type language, which I will show you about later on when we get there. But effectively what you can do is you can attach properties, or you can attach conditions, predicates, to any collection. And what it gives you is a collection, an index collection, which is a subset of the overall collection. And you can just keep adding these on. So this is useful for things like access control. If you've got a user who's logged on, you know who he is, you know what he's allowed to see, you can actually attach predicates to a user or to a collection that the user can see to make sure that at this level, he doesn't have access to anything that he shouldn't see. So a lot of the security is built in at this sort of level. All right, we talked about the indexes. They represent the unique ID of the content in some form in the persistent store. It represents the relationship between the object and its container. Everything exists in a container apart from the roots. And it also represents the commit state, whether it's committed or not, of the object. So whether it's in persistent store or whether it's not. Does that make sense? I was trying to avoid giving you too much theory and too much sort of rule-based stuff, but is that useful to you? Okay, I'll turn the lights on again. Right, let me show you how this is built. Again, we'll work with the user example and we'll work with the content, the user content example. It starts from an interface. The user, what a user is defined by the interface. Now, the user is a very simple thing. It represents very closely what we've stored in the persistent store. But the contact, the user contact, that is a different thing. That's got behavior attached to it. So that interface we'll define a little bit more, and you'll see how that works. Now, in order to express that interface, we need to connect it somehow to the store that represents it. And like I said earlier, there's just no alternative. We have to be specific about this. So in this case, we're now talking about the users that exist in the MySQL database, which is on our local machine. And in fact, if you're going to have any concept of identity, you have to have a local concept of identity. You can't do without that.
So what if you've got multiple stores all having users in them which could have duplication across them?
Right. In that case, you create one of these for each different store. And then the factory would choose between them, because the collection would know about these, and the collection would know about all of the different sources where these could come from. And so when you looked at the collection, what you would see is all the users in all the stores that was known to it. Does that make sense?
Yeah.
Okay. But at this stage, we've only got the one. We've only got the MySQL. Now, in order for this to be a container, this is going to use this interface, which is, this is a terrible name, it's just right from the very beginning of this project, one-to-many array, which does nothing but implement the array semantics. So what we're saying about this is, here is this indexing, here is this indexing semantics, this is, this is what defines it as a container. So that's actually a very thin interface, but it does mean that you've got a bunch of things which need to be defined. Now, in order to deliver that, we've got this thing called an iterable ADO table. Now, ADO is a wrapper around PIDO. PIDO is not that funny. It's basically an interface to SQL databases. So all of the SQL databases that it knows about are all virtualized through this. It doesn't work very well, but it kind of works. And so what ADO does is it gives us a few layers around the outside just to make it easier to talk to. But there's actually quite a lot of behavior in this. What that's doing is that is talking to the database. It's giving us, it understands what the database is. It understands what the dialog is. It actually implements an awful lot of the array semantics. And what it's left with is fundamentally a null constructor, which you have to define if you can be bothered, a thing called dbQuery, new item from PDO row, and offset set validate. Now, what these are, we'll look at those in a bit more detail in a moment. But what they are is, when you instantiate it, you're saying, OK, I'm going to give you some information to identify yourself. But what I now want you to do is to create a query which will allow you to find all of your children, or all of the things which are contained. Doesn't go off and do the containment yet, but it does allow you to find them. And that can be a large, complex thing, and it can query multiple databases, and it actually can reach back into the DB structure. So this can now talk to things that we only know through the DB system. We don't know where they are in reality. When it runs that query, what it gets back is a series of, in effect, rows, a series of rows which are going to be used to construct. But what the new item from PDO row does is it says, OK, I'm going to find one of these, and I'm going to use it to construct the child object. So the lazy instantiation is handled between these two. Now, finally, when you place a child into the container, you've got to give it an index, or maybe you don't have to give it an index. Maybe it chooses the index. But this is the point at which it says, am I prepared to accept this relationship? Am I prepared to accept this index? And of course, sometimes it won't. So this is the validation check. Now, that is actually a pretty small interface for all that behavior. I'm pretty pleased with that. And I will show you the code. I mean, the stuff that you were just seeing on the business layer, I'm going to show you this code on a single page of one of these slides. So it's, it is effective. But a user is not just a container. It doesn't just contain things. It also is contained in its own right. So the fact that something is contained means it has a committable interface as well. And this is part of what we're looking for. Part of what the validate does is it checks that what we're trying to index is committable. Now, the committable is actually not as scary as it looks. We have a commit function, and we have an uncommit function. And the uncommit function can say no, or it can say, right, I'll do it. We have a whole bunch of different constructors. And the reason for those different constructors is because those constructors are part of what are interfacing with the lazy instantiation. So we can construct from a pure user ID. just the key. We know nothing about it except its key. And at this point, it's now a constructed object, even though it's not fully instantiated, but it is in memory. But it now knows enough from that to be able to go and instantiate itself, fully populate itself from the persistent store if it needs to.
Sorry, so if it's in an email address and then you've got multiple repositories with different passwords, how do you know which one that's referring to?
Because if you've got multiple email addresses, if you've got an email address, the password for that email address will be somewhere in persistent store, right? If you've got the email address, then you can use that email address to go and get it from persistent store. Is that the question that you're asking?
So you need both, basically, if you've got them across different stores?
Yes, but you see, if you've got it across different stores, then you're going to have different versions of this. So if you've got one store in a local MySQL, and you've got another store in a remote MySQL, then each of those will know how to access its own database. So that's why you've got to multiply these.
If I have 3 data sources that represent different parts of the conceptual model of my user.
Yep.
Suppose my user has 10 properties, but then there's 3, 3, and 4 across 3 different data sets. Which thing in this model is compositing that data into a single view? Where's the data virtualization and federation?
Can you give me a for instance?
So a user has a username,
Yep.
first name, last name, phone number, email address, postal address. Each of those entities are separated across different data stores. Your conceptual model of that user, how do you composite that data from 3 different sources in this model?
In general, I'd suggest that that's a very weak design, and I would try and coalesce those somehow. But if you are stuck with that, then what I would say is that this thing here would aggregate a series of data stores. So you would have one of these for the name, one of these for the nickname, one of these for something else, and then you put them all together into a single container, and then treat that as your object which you expose to the business layer, but the individual ones are the ones which are active in this term. You're frowning.
Isn't data virtualization and federation about just what I described? It's about gathering data from different stores, combining them into one conceptual view.
Absolutely. But what you're assuming here, in the question that you asked, is that we are trying to enforce constraints across all 3 separate repositories. So if we've got a user ID here with a nickname, and a user ID with a real name, and a user ID with an email address, then we want to keep those consistent. What you're not saying is that you want these to have any kind of relationship to each other. These are in lockstep. Now, you can represent it as a relationship. You could say, all right, well, we have a user and he has a whole bunch of email addresses, and here they are in this table. But in that case, those email addresses would be the contained objects. They would be the children. On the other hand, if you're saying that what we have is in effect one row distributed over 3 tables, well, in that case, you'd aggregate into here. That makes sense?
Yeah.
Okay. Right, so if all we have is the ID, if all we have is something to begin the process of recovering it, then we've got that. On the other hand, we could take an entire row, and an entire row is pretty much everything you need to populate it, not just the ID, but all the other properties. So that's what's defined here, and that you can also get from that. But sometimes you will instantiate this way, and sometimes you'll instantiate that way. And if you've only got this and you start looking inside it, then it will fully populate itself as needs. At this point, you already have the set of tables. You already have the set of rows. You already have the result of the query. So you don't actually have to keep going back to the database to instantiate these. You've already got most of what you need to do this already streamed, or certainly already prepared in the database. We can instantiate it just from initial properties. Now, what we're saying here is that the initial properties, it's different from the row. The row is the complete set of properties, including its ID. This is the complete set of properties, excluding the ID. So this is the way we create something in memory uncommitted. And then finally, it is always legal to produce a null object. So we're saying it is a user contact, and that's all we know about it. We'll fill in the properties later on. So for a child, it is always valid to to produce a null.
What happens if you create a null? What happens if you create a null object and then try to commit it? Can commit fail? Because you said uncommit.
If you try and commit it and your repository refuses to accept null fields, then it will fail.
Right, okay.
But what else would you expect it to do?
Well, just wondering.
Okay. Finally, there's one more thing, and that is the immutable attributes, which is that stuff that I showed you for the filtering. That's something which you can mix into this. I wonder if other languages have anything quite like this. The PHP traits have this thing which is sort of like a textual substitution, but not exactly. But what this does is it just adds a chunk of code into this to handle the attributes. But this doesn't need to know anything about the underlying structure. It just needs to understand what the attributes are. And you just drop it in. The reason why it's optional and the reason why it's not part of this, or the reason why it's not elsewhere, is because when you do drop it in, then it adds a bit of overhead. And if you're not going to use it, then there's no point in having it. So this is an entirely optional thing to put in. And later on, if you like, we'll have a look at some of how some of that works. So any questions about that? Oh, that's good. All right, what we'll do is we'll have a look at some of this, and then we'll have a look at some of that, and I'll show you how it works. First of all, this is the container. So you can see the query is really simple. Again, we're assuming that all of this is coming from one database, but you know, of course, you can extend these queries as much as you like. So up here, this is just simply the select statement which looks for the user contacts. In fact, it's only the user emails. If you've got other types of contacts, then that's going to select from all of them. But all it's doing is returning the query. It's not actually running the query. The running of the query happens in the framework. By the time you get down to here, if you actually start using one of these children, then this is the thing which instantiates it. By now, it's separated out the row. If it needs to do some massaging to create a coherent row from lots of different sources, then it's already been done for you elsewhere. But that's fundamentally the point at which the thing's created. And here is the point at which you validate it. All we're doing here is we're checking that what we're adding really is a user contact and isn't something else. So it's a simple example, but it is really simple code. Now, how does that come out in a user contact? Now remember, the user contact at this point is just committable. We're doing nothing except, well, you know, once it's there, it's a leaf. So from this, when we can create it, and you've seen, we'll see some of the constructors in a moment, but once you've created it, you now need to commit it against an index. So the commit tells you where you're trying to attach it to, it tells you where you're trying to attach it to, and it tells you under what index you're trying to attach it to. So the first thing we do is we check that it really is a sensible index. In this case, that it's a sensible email address. Then we talk to the database, which in this case is still the MySQL, and then we return the thing that we've created. We return the index. Now, it may be the reason for this return is that this may have changed in the way. It may have to massage it. If it's got to rectify an address, then it's allowed to do that. And what it sends back is the corrected version. And you'll see a much better use of that in a moment. Here is the uncommit function. Again, dead easy. It tells you what you're trying to uncommit. At this point, this object already knows what its index is. If it's got one, then it'll uncommit. If it hasn't, it balks. Nice and simple. And this tells you that it tells the system that it's uncommitted. So once it's now out of the database, this can now unlink it from the object model elsewhere in memory. Make sense? So this is what it looks like from the user contact. Now let's look at the user. Remember, the user is also committable because the user exists in that user's all collection. In fact, it exists in quite a lot of collections. So this is what this looks like. First of all, we will never delete a user. So what this says is that if you try and uncommit, it will simply refuse, and the exception is going to bubble back up. The commit Now, remember the user is indexed against an internal primary key, an internal name. In fact, in the model, that's not typed at all. It just happens to be a number because it's MySQL, and MySQL likes integer keys. But when we commit it, we don't know what the key should be. This is being provided by this function. So what we do is we demand that the index that we're trying to connect it to is null. And if we try and give it anything, it's a fault. Then we make the commitment, and this stuff is the sort of thing that's provided by Ada. Just makes it easier. If it has any children waiting to be committed, this cascades the commit onto them. So we can create a user, add some emails to it, and then commit them all in one go. And this is actually an atomic operation, all inside one transaction. So if one goes, then they all go. So that cascades the commit. And then finally, it returns the user ID that we've got here. So this is the point at which it gets to be knitted back into the in-memory structure. Does that make sense? Okay, so again, what we're looking at here is quite a lot of behavior going on, quite a lot of confirmation going on, but pretty simple code to express it. Now, just for completeness, here is the support stuff. Again, this is for the user. This isn't for the user contact. When we invoke it, all we do is return its user ID, and the user ID is just a property that it has to have. The string is instantiated either from the properties or from the repository. And here are the various constructors. And again, they're all pretty simple. Is there anything that you'd like me to say more about these?
So if you've got a team of developers working on creating and maintaining the data model, what sort of governance do you put around it to make sure it doesn't turn into a dog's dinner?
You need somebody who is prepared to take a decision about what the data model is that's expressed at the top of the virtualization layer. Somebody needs to say, these are the objects, these are the indexes, these are the relationships. And that needs to be visible to everybody, and that really is a design process. You can fiddle with it to an extent, but that needs to be under control. Once you've got that, then you've got a series of objects defined. And now you understand what the behavior is. One of the things that I haven't shown you is that all of this is managed through a factory. So when you ask to resolve a user, or when you ask to create a user, or when you ask for the all array, then it's a factory which goes off and constructs that. And largely speaking, that factory is at a global level. It understands all of the separate repositories. But once you've got to that point, then it parallelizes very, very quickly. You've seen these are very self-contained things. Once you've got something which is committable, you can commit it to anything which is prepared to accept it, including purely in-memory arrays. And you can commit to it anything that it's prepared to accept, including in-memory null objects. So that means that things like unit testing is dead easy. And in fact, what we do is we continually run unit suites sitting behind this, just testing these things, making sure that we can load them into memory, get them into database, going and checking the databases with with native transactions to make sure that it's done what we've said it done. And then at the next level up, when we're unit testing the DV layer itself, then in fact there's no expression of the underlying data store. We can test it entirely within memory objects because we've now made the connection. So you've got a great deal of developmental parallelization going on, and you've also got a great deal of tiering of the unitization going on.
But everyone can see they're working towards that high-level data model.
Yes. Yes, the thing which really defines it, the thing which you can't do without, is this description of the object model at the top of the DV. Okay, let me tell you about some of the results that we got with this. Because this was a real surprise when we started using this. I mean, the reason why we started building this way was because we were just faced with all of these different types of repositories, not just different schemas, but different species of storage, and we had to try and unify those. And in fact, this has been very, very successful in these terms. We can talk to pretty much any data source that we want to, and we can do it seamlessly. And that was the point. This is very simple code to write. Even quite complex data stores, even quite complex things, we can write simple code for. And in fact, if we've got time, then I'll talk about some of the other things that we've done. But we have these objects which can commit to two separate collections simultaneously. So we use that for things like permissions. So we can say that this permission, which is a permission object, exists both in the collection of permissions and in the collection of users. And if you delete the user, then all of his permission objects disappear. So we've got that. That happens in a unit, in a single transaction, yes. At the DV layer, at the business layer, then it's literally a matter of deleting the object or deleting the user, and the uncommit cascades. But this idea of this doubly committed object, it turned out to be quite useful. So, very simple code, very short, dead easy to read, dead easy to maintain, dead easy to test. Turns out to be easy on everybody, because once you've got that sort of architectural spec, once you've got that object spec that sits at the top, everything else makes perfect sense. And so it forces you to have this, this architectural specification. This is very flexible. Like I say, the whole point was that we were going to interface to different kinds of data sources. Well, it does. It really interfaces to everything. We could talk to transaction-based systems. We can talk to OpenID. We can talk to single sign-on. Whatever we want to do, we can talk to it. Not only that, it was a really helpful thing to help us migrate. We could construct a database. In fact, at the very beginning of this project, we constructed a really, really simple, horrible authentication scheme, which we would never put on a live system. But it was just a mashup to get us started. Later on, we wanted to get something a bit more secure. It's still not quite there yet, but it's slightly more professional than it was. But what we were able to do was, in the factory, we were able to collect together all of the records in both of them. And gradually, as people were using their accounts, transfer their records, transfer their authentication records from the simple repository into the more complex one. And in fact, one of the things that we found extremely useful was that we had this one test database. This was a website that we put together in 6 weeks. They were going, we're going live in 6 weeks and we got nothing. And so we just flung it together, and everything, there was no database behind it. Everything was done with flat files in the filing system. But we got them live. And then we needed to get this a bit more professional. And so what we did was we installed a DV layer between the existing business layer and the flat files. And then we gradually migrated it underneath. And we managed to do this migration, which was a pretty fundamental change in the nature of what this site was and how it worked. We were able to do this while maintaining full service. I mean, we literally didn't have to take it offline while we were doing this. So it was very successful in those terms. We didn't expect ever to be able to do a job like, or ever to do a job like that. We didn't expect to have to do it, but we didn't expect it to go as smoothly as it did. So we were quite pleased with that. Yeah, now this was something else. When you've got a single database, when you've got a single set of tables, then you can set up a set of constraints between them. As soon as you start splitting it up, then you lose that. I mean, this was the thing with your example, that you've got this user row split between 3 or 4 tables. When you do that, you lose the capability to enforce automatic constraints because the database isn't working for you because you haven't got just one database anymore. But doing it this way, you can enforce it because all of those constraints you can enforce at the DV layer and at the object layer. And you've seen we've got this checking and we've got this enforcement going on. We've got type checking, we've got completeness checking, all sorts of checking going on automatically behind the scenes for you. And then you can use this across multiple repositories. So it does mean that you've got a lot of belief in the systems that you're running, even when they're not even under your control. And again, that was quite a surprise to us how useful that turned out to be. It's not merely a set of trying to tie the tables together. Now this was another thing that was quite interesting. I'll show you in a minute the way it's laid out on disk, because this is quite useful. But the whole of the database stuff is taken off the mapped surface. Now, in a traditional thing, in a 3-layer system, you'll have a business layer going on, and then the business layer will talk SQL to the database. So if you've got an intrusion, then everybody knows where your database is, and everybody knows what the tables look like. Doing it this way, you can't see it. Doing it this way, if you get an intrusion, then what you can see is the DV layer, but you can't see any of the stuff behind it, because the whole point about the DV layer is to hide the stuff behind it. Now this is great because the DB layer is imposing its own security. People can't get in there and fiddle with the tables because the tables aren't accessible. You've got to get, if you're going to get to the tables, if you're going to do some real damage, you've got to get underneath the DB layer. None of that's exposed. So the only way to get into there is a real inside job, and if you don't trust your programmers, then you're in trouble.
What about performance?
I'm sorry?
What about performance?
Performance is very good. In fact, this whole thing is very lightweight. It runs in less than 500 lines because we've implemented it in a number of languages, but one of the things that we did want to implement it in is PHP, and we know that PHP is interpreted. So we wanted to make sure that it would be the database that would limit the performance and not the interpreter. And it's not. The interpreter is pretty quick. That's what you're asking me about, isn't it? Yeah. It is lightweight inside. Again, I can show you some of the code if you need to, but a lot of it's a bit dense, but it is short code. And of course, this is the other thing. A lot of the authentication and the validation is at the point of access. We can create these filters to say, you can't go any further. This is the only part of the collection you can even see. And it means that, for example, if we create a bunch of filters, those filters are about the properties of the objects in the collection, which means that we can create a filtered collection, take a null object, and drop it into the collection. And because that collection is filtered, it populates the object before it goes in. And again, this all happens behind the scenes. This requires absolutely no involvement. So it's very reliable. I mean, it is Jimmy-proof once you build these collections. You know what I mean by Jimmy-proof? Jimmy is the programmer who's just arrived. He's only been working for you for 3 weeks, but he thinks he knows it all. I'm a big believer in Jimmy-proofing code. Okay, again, it's highly maintainable. If you want to know where a piece of access is, there's only ever one place to look. You go straight to it. If you want to know what the access is, there's the line. It's perfectly clear. If you want to know how many different repositories have been aggregated into one point, you go to one point. There it is. At each, there's very little decisions in how to lay out the code from the program's point of view. It actually guides you into the decisions that you want to make. So it's very easy to find the information that you want. Oh, yes, now. Sorry, I keep on coming up with these. One of the problems that we had was we had these growing schemas. We'd start off with very small things, and then we'd add things to it. But we'd have development kits on the desk, and then we'd have a development server, which would have like a pilot system on, and then we'd have a sort of a semi-live system, and gradually we'd pass these across. And we had to keep the tables on disk matching the shapes of the tables that the queries were expecting. Well, this did it, because as part of this process, as part of making the query, then it could say, all right, I can see these rows coming in. Okay, let's put a few more rows in. And so we can actually encode versioning into this mechanism, and as you deploy it, it upversions the tables as you start to use it. And so we suddenly found that all of our table versioning problems disappeared. And in the past, that's always been a right headache, because we've never known what versions we're on, particularly when you've got like micro versions happening. This took care of it for us.
With this inline SQL,
That's right, yeah.
so you're basically adding the columns there.
That's right. So what it would do is it would either imply columns, or when you wrote something, then it would make sure that it already knew at this point what columns were there. So if it had to add columns, then it would. Or if it had to add new tables, then it would. Because at the point of use, then it knows how to fill the defaults in. So it already knows what's there. So it's not already doing any sort of complicated transactions. It's not wasting a lot of time examining it. By the time it needs the information to do the update, it's already got it. So again, these updates were happening for pretty much zero overhead. All right, that's pretty much all I've got about this. I can show you some code if you're interested. I can show you some layouts on the disk. Is there anything that you'd like to ask me at this point?
So the person who would come up with that DB data model, is that typically be a data architect, a combination of business and architecture, and it requires knowledge of the business side, the business rules, the database, kind of need to know everything to come up with that.
Absolutely. I can tell you how we did it, and I would invite you to tell me how you would do it. But we, in the very biggest project that we've put this on, we had a notion of what it was we wanted to accomplish. And so we knew very clearly what was happening at the top of the business layer. We knew very clearly what was happening at the API, partly because the API also forces us to define what it is. Now, we also had a sense of what we needed to accomplish at the persistent level in order to do that. And we had like architectural diagrams showing data moving from geographic locations. We had this sense of the atoms of our data, which was actually completely different from what was going on at the business layer. I'm wondering if I should give you some examples. This is a project management system, but what we had was at the business layer, we had this concept of projects, we had this concept of templates, and you could create a project based on that. Down here, we had these like little atoms of functionality, which were called deltas, which were packages of operands which were placed into an existing structure, and each one was basically a CQRS instruction to say, add this property. And so this model is utterly different to this, and part of what we were doing with the DV layer was bridging that. So at the top of the DV layer, we said, okay, do we understand what a delta is? So let's try and expose the deltas at the DV layer. What operations do we need to provide on the deltas? Well, actually, damn all, because that's all internally, that's all done by something else. What we did do is we created a concept of a project at the top of the DV, which didn't exist at all in the data level. I mean, there was the name of a project, and that was it. But what the DV did was it constructed a project out of what was in the deltas to deliver it up here. So, and then at the business level, we had even higher control of those again. So 3 very different models of data, 3 very different views, and all of them were important to us. Now, who constructed that? We had people who were experts in data storage and who are experts in data transmission, and also who are experts in regulations. We're in the oil business, and lots of the data that we're dealing with is national secrets, and we literally cannot export it across national boundaries. So we had experts in those sort of legalities, as well as experts in building these big architectural systems at a hardware level. At the top level, we had experts in business systems. The talk that I gave yesterday was about how to tune into the language that the domain experts are talking about. So we used that technique to understand what the domain experts really needed to understand the nature of being a project, and we exposed that at the business layer so that we could put different kind of clients on. Bridging the gap, creating the top of the DV layer, that was pretty much down to software guys. It was down to me and a couple of other people who were understanding how we needed to access these underlying atoms. So it was a contribution of a lot of people.
But you needed either side of that to be pretty much sorted before you could do the DV.
I am a believer in pre-planning, and this is a big project, and so we did need to pre-plan it, for sure. But I think that it's a measure of the success of this approach that we were able to plan it in this way, because what it enabled us to do, we could take these 3 very different views, we could get a handle on these 3 very different views, but then we had a series of relatively small steps to translate between them. And so it meant that the various experts that we had available, we didn't need to put them in a room together and bash all their heads together until they came out and somebody conceded. We were actually able to resolve all of these different views at the same time. And I think that was, I actually don't think we could have done this project without some kind of architecture like that. And again, the presentation layer at the top was also part of that, because we had to be able to deliver this internally, we had to be able to deliver it to partners, we had to be able to horizontalize and white label it. We couldn't have done that without this completely separate idea of a look. I was talking about going across poor bandwidth and using the bandwidth you got available. And the same sort of thing is true there, that until we understood really what the data requirements were, we didn't understand how to design that resolution process. But once we'd understood it, then we had this layer which allowed us to do the translation in a relatively small step. Does that answer the question that you're asking?
Just to get an idea, I mean, what's the number of tables, the scale, and how long did it take? Because obviously, if we're starting from scratch, trying to implement even some of the concepts that you're trying to, obviously I'm not looking for like a step-by-step mistake, but what are we talking about in terms of resources and time that would be required to try and implement what you've been saying?
Okay, for the benefit of the camera, you're asking how long is a piece of string?
Yeah, but the thing is, we just need a basic comparison, because basically we've got loads of databases. There's no way we're going to implement all of that in one go and just say there's going to be one unified point of access for all the systems we're going to do. The only way we can actually do it is just like do it in stages, if possible.
Yes.
And run the risk that there could still be other applications updating the underlying data, not through the virtualization layer.
Yes. There are several ways to answer the question. The first is that I would say that no matter what you're doing, building this virtualization layer is going to slow you down initially. I mean, if you can write a business layer and talk SQL to the underlying database, that's faster than building an intermediate stage. Hacking around at a business layer, talking to 3 or 4 different databases, at this point, now you're in profit doing it this way. By the time it's really starting to grow, by the time you're having to debug the business layer because 30 different transactions are all bashing the same table and one of them's got it wrong, by the time you're getting into that kind of debugging, then I would say that you're in profit on the very first table. Because that whole layer is validated away. That you just don't get those sorts of bugs. This does build very reliable systems. Reverse engineering, I haven't done a big reverse engineer. I've done a small one. It was of the order of 20 tables. It took about 2 weeks. And that was modifying the business layer, creating the DV layer, and talking to the existing, they weren't tables, they were flat files, but talking to them. Once I'd got that done, then I could create the new tables in the new database incrementally, and I mean, I wasn't even keeping an eye on that because it wasn't on a critical path or anything. That was just quiet and simple. So I think the answer to the question that you're asking is this. It looks like it's a bit more hard work up front, but actually your payback comes downstream. Your payback comes when you have less debugging, it comes when you have much, much simpler maintenance downstream, and it comes when you have clarity of what it is you're trying to make, because you now have clarity of your data model, and you also have clarity of how that model is being implemented by the schema. Does that answer your question?
Yeah, it does. I suppose I've just got a specific problem in mind, which what's happening in our company is like, so not the example where you've got like one shopper row that's been split across 3 databases.
Mm-hmm.
Throughout the years, we've had different applications. They all decided to keep their own customer table. We want to have an idea of maybe unifying that. I'm just wondering, would this be a way of actually trying to do that? So if we had a data model where customer was like replaces the user representation that you had there, and you somehow, so answering I think that gentleman's question you mentioned, you would amalgamate all the data first within that class and then apply the architecture that you mentioned.
No, I think my prescription for you would be different. Again, let me play it back to you. What you've got is you've got lots of redundant tables, all storing pretty much the same data in slightly different forms.
Yeah, so each application might have stored something slightly different, like in some cases they had salutation and first name or something, but in the others they were interested in the last name or something. But ideally you want a unified customer table so that all applications access to one source rather than it being spread in multiple places.
Yes. Now, in that case, that's very similar to his problem. What I would say is that what you have is you'd have a single user object, and it would go and collect its data from the 3 different tables. Its job would be to resolve the indexes and to create a single index. So at some point, you're going to need a resolution table. It's obviously going to have to, there's going to be errors in these tables, there's going to be inconsistencies. So part of its job is going to have to resolve the inconsistencies. And this tool won't help you do that. You're going to have to do that yourself. But at least it can tell you where the inconsistencies are, and it will allow you to impose the rules to resolve them. But yes, this is exactly the sort of situation where you'd say, I want one collection representing all of my users across all of these separate little tables, which are all slightly different. Yes, it would certainly unify those into a single collection.
Assuming long term, if your goal is to try to actually consolidate those into one system,
Yeah,
this kind of gives you that level of separation between actually what your new applications are doing versus what your older doing.
In fact, you can leave them separate if you want.
Yeah, I think in reality there's no way we're going to physically combine all the data. So what we're going to try and do is add that layer between where things talk to it, and it goes, if you need salutation, it knows where to look to get it.
Yes.
But it's probably just trying to get that one centralised view in the first place, which is one of the key challenges.
That's right. And again, that's an example. You said, if you want to know what the salutation is, but you're only going to want to know what the salutation is in certain uses. So if you actually don't need to hit the tables, then it will know that you don't need to hit the tables. And so that's one, if you need the salutation but you don't need their gender, then it will only do the one transaction, if you set it up that way. But it gives you the space to do that. Anything else I can show you?
Are you putting this presentation up on the website?
This should be available. This is on your stick.
Great.
At least that should be on your stick. If it's not, let me know. Must be address. Anything else I can show you? Well, we have 50 minutes to go. I can show you my juggling. Let's go and have some coffee. Thanks, folks.